can, okay, I need light in between, but I'll put it on. It's fine.
Leave it on.
No, you can put it off.
Okay, but just tell me, I'll switch
Yeah,
it on.
sure.
I'll switch it.
So thank you, it's a pleasure to speak in front of so many sky enthusiasts, and that too speaking about my favorite subject of life and death of a star. Not so much about the life though. My entire research career is based on death of a star. So I'm so much obsessed with this death that my colleagues used to call me undertakers of stars. And yeah, Dali's this Dance with the Death picture in the right shows it remarkably well when time stops and melts into continuum. Right, so talking about stars, I was a bit late in clicking this picture in Zinquazi, but I hope you can see a star in the sky, right? Yeah, good. So, this is our nearest star, and we know a lot of things about the star. Oh, so, hang on. How did it got stuck? Right, so this is the picture of the sun. I included this picture. It was taken last year from the Indian satellite Aditya, which went to one of the Lagrange points in between sun and earth. And if you're wondering, Lagrange point is the point, there are 6 Lagrange points where the gravity of earth and sun exactly cancels each other. So this satellite is sitting over there and taking pictures of the sun. Of course, it's a filtered picture, but right. So what do we know about the sun? We know quite a lot of things rather. The interesting part is this mean distance from the sun, which is around 149 million kilometers from Earth, this was actually known in around 300 BC by this group of people, Eratosthenes and Aristarchus, both from Alexandria, both pupils of the great Euclid of Alexandria. And this is what I am talking about, 300 BC, just after can you put the light? Alexander the Great died. Now we must be wondering at those age how one can actually calculate this mean distance. I'll just give you an instance. So this geometer, Eratosthenes, he knew that there is a place, he used to stay in Alexandria, there is a place, Cenes, around 500 miles south of Alexandria, nearly on the same longitude, where there is a well, a narrow well. And every year on 21st of June, exactly on that day, at 12, at midday, you can see the reflection of the sun inside that narrow well. Every year, the same day. Which means what? The sun is exactly on the top of the well. Fine. But this is not in Alexandria. This is in Cenes, 500 miles south of Alexandria. So what this fellow did, Eratosthenes, on 21st of June, he calculated the angle the sun made exactly at the midday from the zenith, standing in Alexandria. Now you must be wondering, how can you calculate the angle it's making with the zenith? Very simple. Put a long rod in the ground. If the sun is exactly above, where will be the shadow? No shadow. But if the sun is making a small angle, there will be a shadow. And you can calculate the length of the rod, you know. Length of the shadow. Simple trigonometry, you know that. I mean, if you remember Conan Doyle's Musgrave Ritual, the poem. Where was the sun? Over the oak. Where was the shadow? Under the elm? Something like that. So from there, he calculated this angle to be from the zenith. I drew it much bigger, but a very small angle, 7 degrees, around 7. Now the calculation is absolutely simple. And he was calculating the radius of the earth. So if 7 degree means 500 miles, how much 360 degree would mean? That is pi times the diameter of the earth. And from there, he calculated the diameter of the earth to be around 8,000 miles. Within a few percent error, believe me. This is 300 BC, before GPS, before YouTube, before TikTok, before Elon Musk. Just by a stick, he could calculate the radius of the earth. Now the other fellow, Aristarchus, he had a brilliant idea of how to calculate the distance from earth to moon. And his idea goes as follows. Let me just open this. So suppose you hold a disk of 1 inch radius in front of the sun like this. Of course you cannot see the sun. Then move this disk, okay, don't do it with the sun, you'll spoil your eyes. Then move this disk towards the sun like this, exactly on the straight line. There will be a point on which you will see it exactly covers the sun, the sun will see, and if you move a bit further, then you can see the sunlight hitting you. So this point where it exactly covered the sun, what he found was around 9 feet. Remember, this is 1 inch and it has to go around 9 feet to exactly cover from your eyes. So 9 feet means 12 times 9, 12 times 9, 108. So 108, so the ratio of this diameter to how much it should go to stop the sun, exactly cover the sun, is 108. So since this ratio remains constant, now think about this. This is the earth whose diameter I told you around 800 miles, 8,000 miles, sorry. And during the during the lunar eclipse, then this maximum length of the shadow will be 108 times 8,000. That is this distance to the cone of the shadow. Perfect, he didn't stop there. And so immediately when he calculated that, he knew that since we can see lunar eclipse, the distance of moon to the earth cannot be more than this distance. It has to be less than this distance. Okay? But now how to calculate this distance? What he saw was when the moves into the shadow, this distance, he just calculated the time, is 2.5 times the moon's diameter. With this data, and believe me, with high school geometry, he could calculate the distance of moon from the earth is 108 times 8000 divided by 3.5. 2.5 plus 1, yeah. And voila, bullseye. Less than 10% error. And then, how to find this mean distance from Earth to Sun? Again, equally simple. Just now, Kurvashin was talking about phases of the moon. So this is the Earth, this is the moon, and somewhere here is the Sun. Now we know when moon is this side is the new moon. When moon comes this side is the full moon. So in the quarter phase, when the moon is exactly half, it's somewhere here. And then this is a tangent. And whenever there is a tangent and a radius, it's a 90-degree triangle. Pythagoras theorem. So we know this, how much is Earth to moon. And if we can calculate this angle, which he did calculate to be 87 degree, that was a bit off. It is actually 88 point something, but anyway, this is 300 BC once again. And from there, he calculated the distance with an error of 10%. Now imagine in a million kilometer an error of 10% is nothing. I just talked a bit more on this just to show you what is the power of geometry. Perhaps you all have received that meme that goes on social media, especially before the metric exams every year. That why should we study geometry rather than how to calculate taxes? And my reply to that is, studying geometry makes you at least pay taxes because SARS has a lower cutoff. Right, now you can now put the light off. So then we knew the volume. To know the mass, of course, we had to wait till 16th century when Newton wrote the second part of his book, De Mundi Systemate. And there he gave the famous Newton's law of gravitation. So what is the source of solar energy? This took more than 100 years for people to understand. They started with, believe me, there is coal burning in sun. From there to coming to a hydrogen bomb, it took more than 100 years, but then people did understand. And what exactly happening here is 4 protons, that means hydrogen nuclei, they are coming together with a very high speed to become a helium nuclei, you can see. But what is happening? The mass of these 4 protons, if you sum them up, is slightly more than the mass of the helium nuclei that is there. Now what happens to this extra mass? You all know the famous E equals mc square. So whatever the small of mass is, the velocity of the light is 3 times 10 to the power 8 meter per second. You are squaring that, so 9 times 10 to the power 16 meter per second. So that means that is billion is 10 to the power 12. Quadrillion, yeah. So 90 quadrillion times the mass, so you can imagine how much energy is being produced there. Just to show you, this was the famous Operation Castle. the largest hydrogen bomb US ever detonated. It's in one of the islands in Pacific. Of course, don't ask me what happened to the island. It went down forever. So this is one hydrogen bomb. Just to give you the numbers, this proton-proton chain or one hydrogen bomb occurs 9.2 into 10 to the power 37 times, which is, you will learn a new word today if you don't know, 100 undecillion. Each second in the core, converting 400 undecillion proton to helium nuclei. So next time when you go and put your wet clothes on the washing line, remember what nature is doing to dry your clothes. This is no joke. Okay. Oh. So how are stars born? So let's start with that. So when large volume of hydrogen gas collapse under gravity, then the stars are born. So you can see in the sky there is hydrogen gas like this floating, which comes together in its own gravity slowly. And okay, there is no sound, but it's fine. You can have the visual and see that.
Prof, connect it.
Oh no, it's fine. It's okay. So you see, as the gas is coming together, the center is getting heated up slowly.
Is this a time lapse?
It's a time lapse, yeah.
How many million years?
Okay, around, say, less than a billion, the whole process. You see, as the center is getting hotter and hotter, it's throwing out jets of energy. It's still not a star, by the way. It's called a protostar. But ultimately it becomes so hot that this proton-proton reaction starts. As soon as this hydrogen bomb thingy starts at the center, that's the birth of a star.
What's spewing out there?
Whenever things move in a very high speed, it throws away jets of energy in the perpendicular plane. That's exactly what is happening here. And now you can see in the core, the proton-proton chain has started, and yeah. Here is your absolute new star. If you look at it in Sagittarius constellation, you will see there is a nursery there called a stellar nursery of all these newly formed stars and newly forming stars. Okay. So once the stars are formed, more or less they follow the same profile as our sun. By the way, our sun is quite young. If you rescale the stellar age from 0 to 100, our sun is 30 years old. A young man, dynamic, kind of. So during the main sequence or main life cycle, there is nothing dramatic going on there. It's just a star, and maybe if it wants to have a family, it can have a stellar system, that's fine. But the dramatic thing happens when the star goes to the deathbed. So as I said, the definition of the star is this hydrogen bomb must be there in the core, which is giving you all the energy. Now what happens if this hydrogen gets over? Because the hydrogen is turning into helium, right? So So finally in the core, when all the hydrogen turns into helium, now of course the star cannot go to a gas station and say, please fill me up. So once the hydrogen is converted to helium, the fusion in the core stops. Because it takes really more energy to merge to helium to make a carbon and things. So when the fusion in the core stops, then the fusion starts in the outer shell. And that exactly what is the onset of a red giant phase. So for example, you see this is the sun now, 4.6 billion years old. It will continue to be like this till about 10 billion years, then it will start expanding, and finally, how much will it expand? It will take Mercury, it will take Venus, it will take Earth, and just stop in front of Mars. So just to give you an idea, this is the Earth, the Sun now, and this it will be in its red giant phase. Now, as Purvashan was talking about, a lot of red giants in the sky, which you must know. One of the most important one is Betelgeuse, of course. It's 643 light years away, and its age is 7.3 billion years. One of the largest red giants we can see in the sky. Not the largest, one of the largest. And the interesting part is the light takes 643 years to come from Betelgeuse to us. So we don't even know if it has died or not. Because the light which we are seeing now was emitted in 15th century. So if it has died in 19th or 20th century, we still don't know it. We are seeing a ghost. Then Aldebaran is another red giant. So there are quite a few red giants in the sky. So after red giant phase, what happens is this outer layer, this outer red layer, it just burns off, and then what remains is the inner core, which is nearly the size of the Earth. And this inner core, because of its electron there is a lot of electrons in there which pressurizes the inner core. It's very, very, very bright. And it's called a white dwarf. It emits a white light. And then, as you can see, around 12 billion years later, it slowly dies down from white dwarf to brown dwarf and cools off. And then it's just a rock in the sky. That's all. But this rock has a very interesting property. Yeah. At the center, it has iron and then all the other heavier elements as we go towards the outer layer. And you know why at the center it's the iron? Because iron is the stablest nucleus among all the periodic table, all the elements. So, if you are wondering how the other elements are formed, it's formed like this inside the stars, and then they went around the universe. Okay, so white dwarfs in the sky. Just go out any day, you can see Canis Major, Sirius. People say it's the brightest star in the sky. It's a two-star system, Sirius A and Sirius B, and one of them is white dwarf. That's why it looks so bright. Right. Now, what happens if this white dwarf's mass is so large that the self-gravity pushes it more and more? It's like just squashing a balloon. If you go on squashing a balloon, what will happen? It will burst, right? So same thing happens if you just squash, if the gravity squashes the electron pressure, then suddenly the whole thing has a huge explosion. It's so huge that it can radiate as much energy as the sun is expected to emit over its entire lifetime. For example, this explosion occurred in Crab Nebula in 1054 AD. But if you look at the Crab Nebula with a powerful enough telescope, you can still see the reminiscent of this explosion. So you can imagine how big the explosion was. Right. This is a very nice picture of a galaxy called NGC 1365. You see, the astronomers who do all this research in NASA, etc., they get this kind of picture. So you need to know how to read this picture, very interesting. So this bright spot is the galactic center. It's a huge supermassive black hole, just like our Milky Way has a huge supermassive black hole. So this is the galactic center, and you just look just above the galactic center. You can see a spot which is getting brighter and brighter and brighter, and then slowly dimming once again. So that spot is a supernova, and these are from 28th October 2012 to 17th January 2013. So in a month, it has the explosion and then it slowly dimmed down. Okay. So what happens after the explosion? Nearly the entire star goes away, and what remains, the core, is called the neutron stars. That's the densest and tiniest stars possible. How much density is? It's a common question. How much weight does one teaspoonful of neutron star has? Any guess? Why? 1 million tons. 1 teaspoonful of neutron star is 1 million tons. So that's how dense it is. And some of them are, of course, rotates extremely fast. They are called pulsars. So just to show, that's the map of Manhattan, and this is neutron star. So it has a radius of 10 kilometers only. Around the size of Glenwood, maybe Westville. Right. So now what happens if the neutron star has a mass, the general mass of neutron star is around 2 to 5 solar masses. So you can imagine 5 solar mass packed into a 10 kilometer radius. But what happens if the mass of the neutron star is more than that? Very interesting, in 1923, a 24-year-old guy, the same age as our honor students or early master student, he asserted that there is no force possible in this universe that can stop the whole thing to collapse to a point. His name was Lev Landau. Then later on, of course, many other people like Chandrasekhar, etc., they all agreed to that. So if this mass is more than a critical mass, there is no force possible in classical physics, quantum physics, etc., that can stop the entire thing collapse to the central point. And that is the catastrophe that makes a black hole. So how do you visualize a black hole? For me, I feel visualizing it in terms of a whirlpool always helps. Now, black hole, you can see the whole star collapse to a point. So the gravitational force is so high, nothing can escape from nearby, not even light. So just imagine you are a small ant in this whirlpool. Who can swim? That's fine. If you are far enough, it's fine, you can swim to safety. But after a critical distance, even if you can swim really fast, the water will suck you in. And that's exactly what happens in case of a black hole. So just imagine, instead of water, is just space and time on which you are, on which you belong to. And what happens in black hole, that's in the Einstein's theory of gravity, the entire space and time collapses to the central point. So I am standing on the space and I am moving in time. But if the space and time itself collapsing to a point, like that water in the whirlpool, there is no way I can escape. And that's exactly what this thing is. Right. So this is an artist's impression of a black hole. You see, black holes are never that black because there is always stars around, and black hole being so powerful gravitationally pulls the stellar matter which moves around it, make an accretion disk, and finally falls into the black hole. Right. So how many people have watched this movie? Interstellar?
Definitely.
This movie has a very interesting history. The director, Christopher Nolan, wanted to show a very realistic black hole. So what he did was he contacted Kip Thorne, famous physicist who got the Nobel Prize because of the gravitational wave detection, to supply him with the main equations, which Kip Thorne did. And what Christopher Nolan did, he put all these equations into the computers and turned out 800 terabytes of data to solve them. And what he found out was very interesting. Black holes are not actually black. So you see, this is the accretion disk in the front. What are these rays of light? These are actually the accretion disk from the back, but light as it is coming out because of the gravitational pull is bending over, just like a lens effect. So the back one is being shown from the top and bottom. So this is exactly the most realistic black hole looks like this. And how do we know that? Just after that Event Horizon Telescope snapped a picture of the black hole. Now we must ask, these two doesn't look very similar to each other. How can you say they are the same? The reason for this is the Event Horizon Telescope was taking the picture in radio, and this is invisible. Just to show you what is the difference between the two. This is a picture of the same face in different wavelength. So you can see in radio it's all blurred. All you see is there is something here. In microwave, a bit better, it's looking a bit spooky. Infrared, this is the visible one. Ultraviolet, you can really see even the pores of the face, etc. We all know how X-ray looks like. And beyond that, gamma ray, you won't be able to see anything, it just passes. So this was the difference. picture is taken in radio. This invisible. This prediction was invisible, but you can actually see the central dark, and everything looks quite at par. Right. I guess you already know where we as South Africans stand in all this. You are planning to go here, by the way. And so, just to give you a heads up, it's the largest single optical telescope in the southern hemisphere. It has a primary mirror array of 11 meters across, and it's funded by a big consortium of international partners like United States, Germany, Poland, India, United Kingdom, and New Zealand. So this is really something we cherish here. Of course, we have heard about all square kilometer array, and especially the fight we had with Australia in getting the bid, but finally we had the bid. So why so hullabaloo about this? This is world's largest and most sensitive radio telescope. It will sense radio waves from objects millions and even billions of light years away, and will put the dishes not only in the Karoo but in different countries in Africa. So scientists expect that SCA will make new discoveries that we cannot even imagine now. And this project is so big, we are putting a lot of bursaries for postgraduate students, postdoctoral fellows, and people who want to work here. So SKA has attracted a lot of international collaboration as well. And just as a manchi, the SKA project invests, the data collected by the SKA in a single day would take nearly 2 million years to play back on an iPod. Okay, so with this, I stop here. Any questions, comments? Oh, by the way, before I end, in UKZN, the Astrophysics Research Center, as Kurgashan pointed out, has the collaboration with all these faculties, and we have a very, I would say, dynamic research group. I'm just keeping our brochures here. Anybody who is interested to know what we are doing, you are most welcome. Thank you. Thank you very much. Yes.
You mentioned that the neutron star is 3 to 5 solar masses.
Yeah, most of them which we see up there are.
And the neutron star is what's left over after the supernova.
Yeah.
What did it start as? How many solar masses?
The supernova explosion happens for stars which starts with, say, more than 5 solar masses.
So it loses 2 to 3
Yeah.
masses.
Because sun will not go to supernova phase.
Okay.
Yeah, so sun, although it's that big, is one of those smaller stars. So it will die a very silent death, not.
It wouldn't become a black hole.
It won't become a black hole.
How many masses does it need to become a black
To
hole?
start with stars which are around 100 solar mass. Bigger.
100.
Yeah. Yes, please.
Sorry, you said that once two neutron stars are close enough and they create a pulsar.
Yeah.
No.
No, when they are rotating very fast, they create pulsars.
Is it possible for that to eventually become a black hole, or is that?
may not be. If the neutron star is small enough, the pulses are stable enough, they will stay as a pulses. So what gives the pulse of light is basically neutron stars are magnetized. So the magnetic field moving really fast gives those pulses of light, which was detected in 1960s, I think. Yeah.
Sirius A and B are pulses stars.
Sirius B is a white dwarf, not a neutron star. And that's why it's so bright.
Any more questions?
Question there?
Yes.
You touched on the black holes, and I was just curious, how would you best describe, I suppose for everyone here, how would you best describe the black hole information parameters, if that's any way that you have?
Oh, for that you need a bit of a quantum thing. So the point is, in quantum mechanics, information is never lost. So everything has a quantum state. I am not even going there, but you may think the information is lost, but it's somewhere in the system. But with the black hole, the problem is whatever things fall into the black hole, it's lost. The information is lost. That's what Hawking found out, that when finally Hawking radiates out, it has no information of what went in. So you can think about this. For a person generally, what is going in and what is coming out as an excreta. So from the excreta you can know, okay, I have eaten that or something like that. But for a black hole, it doesn't happen. So yeah.
Like as if the information is gone in, gets coded, and we can't read it when it comes out. The radiation.
Yeah, because
it gets.
Nobody knows what happens. That's the whole point. Yes.
So is this like a certain proximity to the black hole? I mean, obviously, something goes in, we're not going to be able to retrieve it from the black hole. So is this like a certain proximity in which?
Oh, that's called the event horizon. So if you're, just like I said for the whirlpool, if you are away from a critical distance, you are safe. But if you are on or inside the critical distance, you will fall. And the problem is, I cannot even give you my cell phone and throw you in, saying, okay, call me what you see. You cannot call me, the signal won't come out. Even light cannot come out.
Sir, I think my question was, is the information that's lost, is it before the event horizon or?
The information of whatever is going in the black hole is completely lost. That's what is the Hawking's information. Yes.
You explained the collapse of the black hole in a way that I haven't heard before, in that there is no force in the universe that can stop that from happening.
That's what Landau said, yeah. A 24-year-old guy.
So that is where the problem comes in with the divide by zero eventually, because all of that goes to a point of zero size.
Singularity. Yeah?
That's called the singularity.
That's
Yeah.
the singularity.
But the point is, even in quantum physics, till now we don't have anything that can counteract gravity. For example, just take, why is not Earth collapsing to a point? Earth has its gravity, right? But the intermolecular forces are balancing the gravity. So Earth is perfectly balanced. But beyond a certain limit, no other forces, no intermolecular, interatomic.
Can we say then that it collapses like at the speed of light, that
Yeah.
you can't escape that, because that's the fastest you can go.
So a black hole isn't an opening to a wormhole.
Very hard to say, because you can make infinite theories. But as Newton said in his Principia Mathematica, book 4, he gave rules of reasoning. You see, Newton was a brilliant scientist, but very egoist, and he was ruthless, basically. In fact, when he was the director of the Royal Mint in his later years, he would go in the night, like we do night patrolling, find out the counterfeiters and make sure they are killed. He fought with Robert Hooke in Royal Society, and he left Royal Society, never set his foot in before Hooke died, and then he became the president of the Royal Society. So Newton was ruthless. He had an excellent brain, but so when his Principia came out, the first edition, people started saying that your logics, we are not getting your logics, etc., etc. So in the 4th edition, he actually added a chapter called Rules for Philosophizing. There he said they are like brilliant rules. There he said what can be called a scientific theory, what cannot. Suppose I make a theory that when everybody leaves this room and lock this room and all the lights are off, then fairies comes and dance in this room. But as soon as you open the room, they vanish. It can be okay theory, right? But never experimentally verifiable. So according to Newton, this is not science. Which I personally philosophically agree. So you can make a lot of theory, okay, if I fall into the black hole, this will happen. I'll get I can eat meatballs and spaghettis or whatever, you can make whatever theory you like. But unless it's experimentally verifiable, it's very hard to.
If there are two black holes that are equal in magnitude, do we have a theory as to what would happen
If they come closer, they will merge and make a bigger gap. And those are the events that now LIGO is watching as the gravitational wave.
If the universe is running down, which is what is happening in the understanding of the black hole, virtually all stars end up either as cold rocks or black holes.
Yes.
Is there no way in which the universe might be coming back again in some other way?
You see, new stars are also being formed.
There are new stars being formed, but that's because of the original.
But what the current theory of universe says, because of this cosmological constant and things are growing apart, accelerating apart, there will be some time when it will start becoming cold and a very boring phase before everything scatters away. So that's, again, I'd say that's one of the theories. In our lifetime of 40 years, we are talking about 40 billion years, right? Which is quite crazy. So all of these are theories, and you will see a lot of new theories with the only thing what people look about is if they are mathematically consistent or not.
The expansion is proven. Correct.
The expansion is proven because you can see the redshift of if something is going away from you, there is a Doppler shift of the distance. For example, I'll give you an idea. When a train is coming to you and giving the horn, how does it sound like? It's increasing. And as soon as it passes you, the frequency decreases, right? So similarly, when stars are moving away from each other, the hydrogen line shifts towards the red. 21 centimeter line, that is the hydrogen line, shifts towards the red. And you know they are going away from each other. So that's how we actually know that the universe is expanding in an accelerated rate.
Anything else? Any more questions?
Fascinating.
Thank you. You have such a dynamic audience is always.
I think you taught us all sorts of things. I mean, not just one thing about the star and everything else. That was excellent. But I do want to thank you for promoting us going to Sutherland.
Oh,
See
yeah.
that? Okay, because it's another, I mean, this is part of what we are doing, we're observing and we're looking, and I think Sutherland is a fantastic place to go to.
Yeah.
Thank you very much.
Pleasure.
Okay, guys, so I think that's all for now.